Hello everyone and welcome back to the C++ 3D game tutorial series. In this sixth episode, we will finally see how to render our first triangle on the screen. As always, we will face three main parts: the requirements, design, and implementation of all the software components required to render a triangle. Let's start with the requirements. We need a C++ IDE. In this series, we use Visual Studio 2022 Community. The target platform is Windows. The target graphics API is DirectX 11. And last but not least, a good understanding of the C++ programming language is recommended. Now we can start the design part. In the previous episode, we learned how to manage the shaders stage of the graphics pipeline. We explored how to write HLSL shader code and compile it using the d3d compile function. Specifically, we created and bound shaders to the graphics pipeline by designing a helpful class called graphics pipeline state. This time, we are going to focus on rendering our very first triangle on the screen. At its core, a triangle is a polygon made up of three vertices. These vertices are essentially points in space, each with a specific position. But in the context of computer graphics, a vertex is more than just a point. Typically, a vertex is defined by a set of attributes that go beyond its position, such as color, texture coordinates, and normals, depending on what the rendering process requires. To dive deeper, we can define different types of vertices based on the attributes they carry. For example, a vertex that only contains positional information may be referred to as vertex pose, while a vertex that holds both position and color could be called vertex pose color. This flexibility allows us to define various vertex types, each carrying the specific data needed for different rendering scenarios. Now that we understand what a vertex is, we need to decide where to position the vertices of our triangle in order to render it on a 2D screen. To do this, we need to understand the steps the GPU follows to transform the vertices and render the final geometric shape on the screen. When a vertex is processed by the GPU, it first enters the vertex shader, where it is transformed into what is known as clip space. Clip space is a special 3D coordinate system where the visible portion of our scene is shaped like a cube, or more precisely, a box. The GPU uses this space to determine what parts of the scene are visible and which parts should be discarded. That's why it's called clip space, because any parts of geometry that fall outside this box will be clipped, or in other words, trimmed away. The output of the vertex shader is a four-dimensional vector in clip space. This means we have x, y, and z components plus an additional component called w. Next, the GPU performs something called perspective division, where it divides the x, y, and z values by the w component. This step transforms the vertex into normalized device coordinates, or NDC, where all coordinates are scaled to fall within the range of -1 to 1. After that, the NDC values are passed through the viewport transform, which maps them to screen space. This step converts the normalized values into actual pixel positions on the screen, based on the resolution and viewport settings. Finally, these screen space coordinates are passed to the rasterizer, which determines how the geometry covers pixels and prepares those pixels to be processed by the pixel shader. With that said, to keep things simple, we would place the vertices of our triangle directly in normalized device coordinates. This allows us to bypass clip space entirely. NDC, or Normalized Device Coordinates, is a 3D coordinate system used by the GPU just before rasterization. It describes the position of a vertex in a normalized device-independent way relative to the screen. For simplicity, let's imagine NDC as a 2D coordinate system with two main axes. The x-axis runs horizontally from -1 on the left to 1 on the right, while the y-axis runs vertically from -1 at the bottom to 1 at the top. So, for example, the point -1 represents the bottom left corner of the screen. 1 is the top right corner, and 0 lies exactly at the center. By choosing coordinates within this range, we can easily define the position of the three vertices that form our triangle. It's important to pay attention to the z value as well. It must be set between 0 and 1. If it is outside this range, the triangle will be clipped and not rendered properly. As we mentioned earlier, it's normally the GPU that computes NDC values by performing the division of x, y, and z by the W component. So how can we bypass clip space in the vertex shader? By simply setting the W component of our 4-dimensional output vector to 1. That way, the GPU divides the x, y, and z values by 1, leaving them unchanged. Since we have already providing values in NDC, this trick allows us to skip the usual transformation steps and work directly in NDC. At this point, we have the final three vertices of our triangle. So, how can we use them to render the triangle on the screen? First, we need to define the corresponding C++ structure for our vertex type. However, since our vertex currently only includes the position attribute, let's keep things simple for now and represent it using a three-dimensional vector instead of defining a full structure. Later on, once we add more attributes such as color, normals, or texture coordinates, we will go ahead and define the structure properly to include all the necessary data. Next, we create a list of three vertices of type vector3 in C++ code. After that, we need to pass this data into a so-called vertex buffer. In Direct3D 11, a vertex buffer is an object that stores an array of vertices in GPU memory. Once the vertex data is loaded into the buffer, the GPU can access this data efficiently during the rendering process. We then bind the buffer to the input assembler stage of the graphics pipeline. At this point, we need to configure some stages of the graphics pipeline. In particular, we need to set the vertex and pixel shaders, which we covered in the previous episode. Once everything is set up, the GPU can pass the data from the vertex buffer into the vertex shader. This is where the vertices will be transformed from a particular coordinate system, such as world space, into the clip space, as we have discussed earlier. Since we have already defined vertices of our triangle directly in clip space, or better said, in normalized device coordinates, no transformation will be necessary in the vertex shader. The vertices retrieved from the buffer will simply be passed along as they are to the next stage in the pipeline. Next, we need to provide the graphics API and the GPU with the necessary information about the format and the structure of the vertex data in the buffer. We do this by creating the input layout. The input layout is essentially a map that tells the GPU how to read the vertex buffer and convert it into meaningful attributes that the shader can use. It's important to note that the vertex buffer, input layout, and vertex shader must all be in sync with each other. If we change the format of the vertex structure, such as adding new attributes or changing existing ones, both the input layout and the vertex shader must be updated to ensure that the GPU processes the vertex data correctly. Now that we have set everything up, we record the draw command in the command list using the device context. Once the GPU processes this command, it begins executing all the stages of the graphics pipeline, using all the data we set up earlier. As we saw in the previous episode, The vertices, once transformed in the vertex shader, are assembled into a geometric shape during the primitive assembly stage. The geometric shape is then rasterized into a 2D image made up of pixels in the rasterization stage. One important note here: before rasterization can take place, we need to set the viewport. The viewport defines the area of the screen where the final image will be drawn. Finally, the pixel shader is executed, which calculates the final color of each pixel. If you have any questions, doubts, or comments about this episode, feel free to leave them in the comment section of this video or on the Discord server. You can find the link to the Discord server in the video description. Also, if you find these tutorials helpful, please consider supporting their development on Patreon. Every contribution makes the difference, no matter the amount. Great, we have gathered all the necessary information to start the implementation. Let's start by creating the vertex buffer class. As usual, we will move both the header and C++ files into the graphics folder within the source directory. Once that's done, we can start by wrapping our class inside the DX3D namespace. Next, we will make the vertex buffer class final and extend it from the graphics resource class. To provide the full definition of the base class, let's include its corresponding header file. Now we are ready to add the constructor. The first parameter we will add is a constant reference to the graphics resource descriptor. We can then implement the constructor. As usual, we replace the default include path in a way that matches the path style used in the other source code files. At this point, we need to call the graphics resource constructor in the initializer list and pass the descriptor parameter. With that completed, let's move on to implementing the constructor. The first thing we need to do is get the D3D11 device and call its method createBuffer. As the name suggests, createBuffer allocates a buffer in GPU memory, whether it's a vertex buffer, index buffer, or constant buffer. Just like with other D3D API calls, createBuffer requires us to pass several parameters. The first one is a pointer to a buffer descriptor, which is a structure that describes how the GPU buffer should be created. This descriptor allows us to define the buffer's size, usage, bind flags, and CPU-GPU access behavior. To define these, we will create a local variable called buffDesc of type D3D11 buffer desk. The first member we need to set is byte width, which defines the size of the buffer in bytes. This must be greater than 0. To calculate the final size, we need a vertex buffer descriptor that provides this information. So let's go to the common header file and create the vertex buffer descriptor structure. The first member of this structure will be a constant void pointer to the vertex list. Then we need to define a member that provides the size of the vertex list, which in this case means the number of vertices. We will use an unsigned integer type for this member. Finally, we need to define a member that holds the size in bytes of a single vertex. Let's return to the vertex buffer class and add another constant reference parameter to the constructor, this time to a vertex buffer descriptor. With this done, we can copy and paste the parameter into the C++ file. Now we can compute the final size of our vertex buffer by multiplying the number of vertices by the size in bytes of a single vertex. This will give us the total size in bytes of the entire vertex list. Next, we need to set the bind flags. This tells the D3D11 device what the buffer should be used for. Since our buffer will store vertices, we will create it as a vertex buffer. Great, now that we have finished setting up the descriptor, we can pass it to the createBuffer method. The second parameter required by createBuffer is a pointer to another structure called D3D11 subresource data. This structure provides a way to supply initial CPU-side data to the GPU resource during creation, which is especially useful when the data is known upfront, like in our case. So let's define a local variable of type D3D11 subresource data called initData. The only attribute we need to set here is sysmem, which expects a constant void pointer to the initial data. We can retrieve this data from the vertex buffer descriptor by accessing the vertex list pointer. Once we have set this up, we can pass the pointer to the initData structure as the second parameter to createBuffer. Of course, to get the pointer to this structure, we will need to use the adjust_of operator. Finally, the third parameter is the output parameter of the createBuffer method, which will hold the final buffer object. To store the buffer, let's go to the vertex buffer header file and add a com pointer to the D3D11 buffer, and let's call it buffer. Then we can return to the C++ file and pass the pointer to this function. Once all that's done, we need to check for errors by using our log throw_on_fail macro. What comes next? As we have seen in the previous episode, we should validate the arguments. In this case, we need to check the members of the vertex buffer descriptor. Specifically, we should ensure that the various members are non-null. If any of them is null, we should throw an invalid argument exception. Now that we have completed that, let's move on to the graphics device header file and add a new method called createVertexBuffer. This method will return a pointer to a vertex buffer object. To do this, let's go to the core header file and start by making a forward declaration for the vertex buffer class. Then, we will define a type alias for a shared pointer to a vertex buffer, which we will call vertex buffer pointer. Next, let's go back to the graphics device class and define the return type of the create vertex buffer method. We will also define the parameter, which will be a constant reference to a vertex buffer descriptor. With that done, we can implement the method. As we did with other graphics resource objects, we will call a makeShared function to create a shared pointer to a vertex buffer and pass both the vertex buffer descriptor and graphics resource descriptor to it. Finally, to ensure everything compiles correctly, let's include the full definition of the vertex buffer class in the appropriate places. This will avoid any compilation errors. Alright, that's it. We can now proceed to the graphics engine C++ file and call the method we had just created in the constructor. Of course, we will need to pass the necessary data required by the vertex buffer descriptor. To do this, we first need to define the list of vertices of our triangle. To define these vertices, we need a three-dimensional vector to represent a point in 3D space. So let's head to the math folder and create a header file called vec3. Inside this file, we can start by adding the dx3d namespace and within it the vec3 class. As with other math classes, we will follow the rule of zero, which means we only need to define constructors and no other special methods. Let's define a default constructor and then add three float components to represent the x, y, and z coordinates. To make sure the F32 type is recognized, we can include the core header file. After that, we can define the x, y, and z attributes. Next, let's define another constructor that will allow us to initialize the 3D vector by directly providing all the components. This will make it easy for us to create vectors with specific coordinates when we need them. With the vec3 class in place, let's return to the graphics engine C++ file. Now we can start defining our vertex list of type vec3. Since we don't plan to modify it once defined, we can make it constant. Of course, we will need to include the header file for vec3 to make sure everything compiles correctly. At this point, we can fill the vertex list with the appropriate values, based on the coordinates we discussed earlier. Specifically, the first vertex will be at the bottom left, the second one will be at the top center, and the last vertex will be at the bottom right. All these values should be within the range of -1 to 1. Now we can pass all this data to the method. We can get the size of the vertex list by using the standard size function, and for the final parameter we need to pass the size in bytes of a single vertex. Since our vertex is just a 3D vector, the size in bytes is the same as the size of our vec3 class. We can easily compute it by using the size of keyword. Next, we need to store the vertex buffer. Let's go to the graphics engine header file and add a pointer to the vertex buffer class. We will call this pointer BB. Once we have this in place, we can use it in the constructor of the graphics engine class. Once that's done, we don't need to do anything else except bind the vertex buffer to the graphics pipeline, specifically to the input assembler stage. Let's go to the device context header file and start by creating the setVertexBuffer method. This method will take a constant reference to a vertex buffer as its parameter. Now we can implement the method. As usual, we will get the deferred context and call the iaSetVertexBuffers method. As the name suggests, this function binds one or more vertex buffers to the input assembler, the IA stage of the graphics pipeline. This is how we tell the GPU where our vertex data is stored and how to interpret it. The first parameter required by IA set vertex buffers is start slot, which indicates the starting point in the list of vertex buffers. Since we plan to use only one vertex buffer for now, we can set this to 0. The second parameter is the number of buffers being passed. Since we are only using one buffer, we can safely pass 1 here. The next parameter requires the actual list of buffers, specifically a pointer to an array of D3D11 buffer pointers. In our case, we are only passing one buffer, so we can define a local variable called buff and retrieve the row pointer from the D3D11 buffer object stored inside the vertex buffer. To make sure the vertex buffer class is recognized, we will need to include its header file. Unfortunately, we currently don't have direct access to the D3D11 buffer, so we will go to the vertex buffer class and make the device context class a friend of vertex buffer. This will give the device context access to the private members of the vertex buffer. Next, we can return to the device context C++ file and retrieve the buffer by calling the get method, which will return the row pointer. The function also requires a list of strides, which represent the size of a single vertex in bytes. Since we only have one vertex buffer, we will define a local variable called stride and retrieve the vertex size from the vertex buffer class. To do this, let's define an unsigned integer attribute called vertex size inside the vertex buffer class. We will initialize this variable in the constructor's initializer list by passing the value stored in the descriptor. Now let's return to the device context C++ file and retrieve the vertex size. As with the previous parameter, we can pass the address of the stride variable. Lastly, the function requires an offset parameter to indicate where to start processing the vertex data. Since we don't need to start at any specific offset for now, we can define another local variable called offset and initialize it to 0. To make sure the compiler understands that we want an unsigned integer value, we can append a u character to the 0, indicating it's an unsigned integer. With that done, we can pass the address of the offset variable to the function. Finally, we are ready to return to the graphics engine C++ file. In the render method, we should retrieve a reference to the vertex buffer. We do this because it's clearer and keeps our code more organized. Once we have the reference, we can call the setVertexBuffer method and bind our vertex buffer to the pipeline. With that completed, we can finally focus on the vertex shader code. The first thing we need to do is make sure the vertex shader returns a float4 value. Additionally, we need to define a semantic for this returned float4 value. Let's use sbPosition. A semantic is essentially a label that tells the GPU what a variable represents and how it should be used in the graphics pipeline. By defining float4 and sbPosition in this way, we are telling the GPU this float4 represents the final position of the vertex. Use it for rasterization. Without this so-called semantic, the GPU wouldn't know how to interpret the return value of the vertex shader. Let's keep things simple for now by returning a basic float4 value composed of ones. Now, what's next? We need to retrieve and process the data from the vertex buffer that we have bound to the pipeline. To do this, we will add a parameter to the VS main function of type float3 called pose. This will represent the position of each vertex. We also need to define a semantic for this, which, as we remember, tells the GPU how to treat the variable. In this case, let's call it position. With this, we are specifying that the float3 pose variable will represent the position of a vertex in 3D space. A float3 is simply a three-dimensional vector composed of three values, x, y, and z, just like our vec3 class. As we discussed earlier, the VS main function processes one vertex at a time, so we are retrieving one vertex at a time from the vertex buffer that was provided earlier. At this point, we can return the pose parameter as it is by passing its three components inside the float4 constructor. So far so good. There is, however, another problem to address. The position semantic is not defined by default in Direct3D. To properly define it, we need to use something called input layout. Let's take care of this in the graphics pipeline state. An input layout defines how the vertex buffer's data is interpreted by the vertex shader. It's the bridge between the CPU side vertex data and the GPU side shader inputs. The input layout tells the GPU here is how each vertex is structured in memory, what each part means, what type it is, and which shader input it maps to. In our case, the vertex is composed of only one attribute, the vec3 position, and we want to map this attribute to the position semantic defined in the vertex shader. Let's create this layout by calling the createInputLayout method. Like other Direct3D API calls, this method requires several parameters. The first one is a pointer to a list of the 3D11 input element desk objects, which describe each attribute in our vertex format, such as position or color. These descriptions tell Direct3D how to interpret the binary vertex data and how to map it to the vertex shader's expected inputs. For our case, we only need to define one attribute, the position element. The first member of an input element is the semantic name, and here we will pass position, which is exactly the same name used in the vertex shader code. The next member is the semantic index. This is used to differentiate multiple variables that share the same semantic name in the vertex shader. Since we don't have multiple attributes of the same type, we will set it to 0. Next, we define the format of the position attribute. In our shader, the position is defined as a float free, so we need to find the corresponding DXGI format for this type. The format we need is the XGI format R32, G32, B32 float, which corresponds to a three-dimensional vector made of three float values, each taking 4 bytes, that are 32 bits. So we are specifying a 3D vector of 3 floats, each 32 bits in size. The next attribute we need to set is the input slot. This tells Direct3D which vertex buffer the element comes from. In most cases, this will be 0. Next, we set the aligned byte offset, which is the byte offset from the start of the vertex structure. Since position is the first and only attribute, the offset will be 0. Then we have the input slot class attributes that specifies whether a vertex attribute comes per vertex or per instance. For now, we are not working with instancing, so we will set it to D3D11 input per vertex data. Lastly, the instance data step rate attribute is required for instance rendering. Since we are not using instance rendering right now, we will set it to 0. With all this done, we have finished defining the first attribute of our vertex. Remember that the input layout must match the vertex structure defined in the vertex shader code. The structure passed as input to the VS main function, in this case the float-free value. So, defining this manually is not ideal. There is a better approach, which we will explore in a future episode, where we will automatically generate the input layout using a feature called reflection. For now, we will proceed and pass the elements list to the create input layout method, along with the number of elements in the list, using the standard size function. The method also requires the shader bytecode, which defines the vertex data structure. Since the vertex shader code defines this structure, we will pass in the bytecode of the vertex shader and its size in bytes. Finally, we need an output parameter, so let's go to the graphics pipeline state header file and add a com pointer to a D3D11 input layout, which we will call layout. We can then return to the C++ file and pass the layout pointer to the function. As usual, let's check the function using our log throw-on-fail macro to handle any errors. With that done, we can now return to the device context C++ file. In the setGraphicsPipelineState method, we can finally bind the input layout we just created to the graphics pipeline by using the IASetInputLayout method. As the name suggests, this function tells the GPU how to interpret the binary structure of our vertex data and how it maps to the vertex shader's expected inputs. It's a critical step in making our vertex data usable by the GPU. We are now ready to move on to the device context header file and add a new method called setViewportSize. This method will define the rectangular region of the rendered target where the final image will be drawn. To do this, we will define a parameter which will be a constant reference to our rect object, and this rect object will hold the size of the viewport. Let's go ahead and implement the method. In the implementation, we will need to call another function of the device context, called rsSetViewports. The rsSetViewports function configures where and how our geometry will be rasterized on the screen. It requires two parameters. The first one specifies the number of viewports we intend to use. Since we plan to use only one viewport for now, we will set it to 1. The second parameter requires a pointer to a D3D11 viewport object. So let's define a local variable of type D3D11 viewport and call it VP. At this point, we need to set several members of this structure. First, we will set the width of the viewport. We should use the size of our window for this, which we can obtain from the size parameter. Since the D3D11 viewport structure expects the width to be a float, we will need to static cast the integer width from the size parameter to a float. Next, we will do the same thing for the height. We will cast the integer height from the size parameter to a float as well. Then we need to set two additional attributes, min depth and max depth. These fields define the depth range to which geometry is mapped after projection during the viewport transformation. Specifically, min depth represents the near clipping plane in depth buffer space, and we will set it to 0. Max depth represents the far clipping plane in depth buffer space, and we will set it to 1. Once we have set all of these members, we can finally pass a pointer to the VP variable to the rsSetViewports function using the address of operator. Next, let's move back to the graphics engine C++ file, and in the render method, we will call the setViewportSize method. Here we should pass the current size of the swap chain. Currently, the swap chain doesn't return any size, so let's go to the swap chain header file and add an attribute of type rect, which we will call size. Then let's add a getSize method that will return this rect object. Let's also mark the getSize method as const and no except, since it doesn't modify any state. Now let's implement the method. As usual, we will prefix the namespace before the name of the return type. The getSize method will simply return the size attribute that we just defined. Finally, let's go to the constructor and initialize the size attribute in the initializer list using the winSize member of the swap chain descriptor. With all of that done, we can return to the graphics engine C++ file, and in the render method, we will now pass the size to the setViewportSize function. The only thing we need to do now is go to the device context header file and define one of the most important functions, the drawTriangleList function. As we have already mentioned, this function is responsible for recording a draw command to send to the GPU. Once the GPU processes this command, the graphics pipeline will be executed. For this method, let's define two unsigned integer parameters, vertex count and start vertex location. We will dive into the meaning of these parameters shortly, but for now, let's start implementing the method. At this point, we need to call an important function called IASetPrimitiveTopology. This function is used to define how the input assembler stage interprets vertex data, specifically how it assembles the data into geometric primitives like triangles, lines, or points. It tells the GPU how to connect the vertices we have sent via the vertex buffer to form shapes. Without these, the GPU wouldn't know whether to draw triangles, lines, or other types of primitives. Since we want to draw a triangle, we will set the primitive topology to triangle least. Triangle least specifies how the GPU should interpret the vertex data. Every group of three vertices will be treated as an independent triangle. In our case, we have defined a vertex buffer with three vertices, so only one triangle will be rendered on the screen. If we set 6 vertices, 2 triangles will be drawn, and so on. Let's go ahead and finally call the draw function. As we have said before, this function records a draw command in the command list. Once the GPU processes this command, the graphics pipeline will be executed. As usual, we need to pass some parameters. The first one is vertex count. As the name suggests, this defines the number of vertices to draw. Let's pass the vertex count parameter here. The second and final parameter is the start vertex location. This parameter allows us to specify the index of the first vertex in the vertex buffer to start drawing from. As before, we will pass the start vertex location parameter. Now that we have defined the draw command, we need to move on to the graphics engine C++ file and call the draw triangle list function in the render method. Before proceeding, it's important to note that we can only call the draw function once we have set the graphics pipeline. The pipeline provides all the shaders that determine how the triangles will be rendered. Next, we need to set the viewport size, which defines the area of the render target, in this case the back buffer, in which the content will be rendered. And most importantly, we also need to bind the vertex buffer to the graphics pipeline, as it provides vertices from which the geometric shapes and raster image will be generated. That being said, we need to pass the number of vertices we want to draw to the draw function. In this case, we want to draw 3 vertices, but we don't know the exact number yet. We should get it from the vertex buffer. So let's include the vertex buffer header file to get its full definition. Unfortunately, we haven't yet defined a method to get the number of vertices, so let's go to the vertex buffer class and define a new attribute called vertex list size. At this point, we can create a new method called getVertexListSize that returns the number of vertices. We will also mark it as const noExcept, since it doesn't modify the state of the object. Let's implement this method. With that done, we can return the vertex list size attribute and initialize it in the initializer list using the attribute provided by the descriptor. We are now ready to return to the graphics engine C++ file, call the getVertexListSize method, and pass the result to the draw function. Since we want to start processing from the first vertex, we will safely pass 0 here. Also, since we are defining an unsigned integer value, let's append the u character to the value. Alright, let's place a breakpoint inside the vertex buffer constructor and in the render method of the graphics engine class. We are ready to debug our program. First, we will check the arguments to make sure everything is correct. Once confirmed, we proceed to define the various properties of the buffer, set the initial data to pass to the buffer, and in the end, we create the actual buffer. So far so good. Let's click continue and move on to the render method. In the render method, we bind the various objects of the graphics pipeline state to the pipeline, such as the input layout, vertex shader, and pixel shader. We then set the size of the viewport using the window size, or more specifically, the size of the back buffer. And finally, we bind the vertex buffer, record the draw command in the command list, and send the command list to the GPU for execution. Let's continue to see the result. Unfortunately, no triangle is visible yet. That's because we still need to write the pixel shader. So let's go back to the graphics engine constructor and immediately start finalizing the pixel shader. Let's start by defining the return type. Here we need to set a float for return type with a semantic called svtarget. Svtarget is a semantic used to indicate the output of a pixel shader. When combined with a float for value, it defines the final color that the pixel shader writes to the rendered target. In particular, the float for value represents a color with red, green, blue, and alpha channels in that order. This is because we have set the rendered target to the back buffer, which was generated with the RGBA format in the swapChain class. That said, we can return an RGBA color. If we set the red, green, blue, and alpha values to 1, we define the color white. This means that we will color each pixel of the surface of our triangle with white. We are now ready to debug our program. And there it is, our wonderful triangle, colored white. We have finished. Before we conclude, let's take a moment to improve the graphics log utils header file code. Specifically, we can reduce the multiple if-else statements inside the failed HR block by using the ternary operator, which we already used earlier with error MSG. Let's apply the same approach here. If we have an error MSG, we will pass it. Otherwise, we will use the default shader compilation failed message. At this point, we can safely remove the else block, and since we are checking the error MSG using the ternary operator, we can also remove the if error MSG block. This will further simplify the code. Next, let's do the same for the warning message. Now, let's recompile the program to make sure everything is working as expected. It looks like everything is fine. That's all for now, folks. Today we learned how to render our very first triangle on the screen. We covered how to create a vertex buffer to manage the triangle's vertices. We also learned how to create an input layout that tells the GPU how to interpret the vertex data structure defined in C++. In addition, we explored how to extend the vertex and pixel shader code to properly process the triangle's vertices and color its surface. In the end, we saw how to set the viewport area of the render target where we have rendered our triangle and how to define the draw function, which starts to execute the stages of the pipeline. The next time, we will dive even deeper into how to manage shaders. Hope you enjoyed this episode. See you soon. Thanks for watching.